Great. So let's see, where is my marker? Got it. Okay, so let's start with today's lecture. So today we'll be, wrapping up the exploration work that we started last time. We're going to look at, offline RL, which will deal with the situation where an agent cannot collect more data, but it can learn from data it has already collected. We'll look at some offline RL algorithms. And finally, if we have time, we'll look at AlphaZero, which is a case study of overcoming exploration with self-play. So where we ended the last lecture was studying intrinsic rewards and how they can be utilized to incentivize exploration. Right? So in particular, what we considered was a setup where we have some environment, we learn a model, and that model helps us give an intrinsic reward. And specifically what we looked at was prediction error as the reward to incentivize exploration. But there can be many other notions of intrinsic reward. For example, we can count how many times an agent has been in a particular state and incentivize agent to visit states which have low counts. And that would mean that the agent would go to new parts of the environment. So we can use learning progress. And there are many other metrics that we can use. So we'll be looking at a few of these other choices for intrinsic rewards. So let's go through some of them one by one. So the first thing which we are going to cover is typically, if you recall what we did in the reinforcement learning assignments, is that for exploration, we had some noise that we introduced in the action space, right? And that noise was in the form of a Gaussian noise for continuous action space, or epsilon greedy in case of discrete actions, where we randomly chose one of the actions with probability epsilon. So instead of actions, to incentivize exploration, one possibility is to introduce noise in the parameter space. Now, what do I mean by this? So typically, the neural network has input X. There are parameters, the weights and biases. This is a fully connected layer. And the output will be Y is equal to WX plus B. So assume that Y was nothing but the action. Right? So typically, what we considered was to add noise in the output Y. So that is how we were exploring until now. But an alternate possibility is to add noise in the parameter space. Right? So we could express the parameters W and B as a mean and a standard deviation multiplied by some noise, which is epsilon. Right? And where mean and so what we essentially end up doing is we perturb the weights for every state that we are seeing by a small random amount. And how small that random amount is something that we can also learn through these parameters sigma. So why would we want to do parameter space exploration instead of action space exploration? And one possibility is that noise in parameter space can help you choose actions which are very different from each other. And what we find empirically is, if we use these noisy networks, they do lead to better performance, with respect to DQN or dueling networks that we saw before, and even with A3C. So these are results which are shown for Atari games. So in general, putting noise in the parameter space seems to be better than putting noise directly in the action space. So this work, if you want to know more about this work, you can read this paper, Noisy Networks for Exploration, in more detail. Any quick questions on this part? I see something coming on the chat window. Let me try to open it up. So would this noisy network be similar concept to the reparameterization trick? So you can think of this as using the reparameterization trick, but the purpose is different. Right? The purpose is to perturb the parameters, right? Versus in VAEs, you use the reparameterization trick to output to model a stochastic distribution. Right? So it is a reparameterization trick, but for a different purpose. And for those of you who don't know about the reparameterization trick, I think it's completely okay. You don't need to know about that to understand what we are covering in the class for now. Any other questions? No? Okay. So now let's look at another notion of how we can incentivize exploration. And this comes by notions of uncertainty. Right? So uncertainty is saying, so we covered two kinds of uncertainty in the last lecture. Right? So one was eleutaric uncertainty and one was epistemic uncertainty. Right? So epistemic uncertainty is uncertainty in my model versus eleutaric uncertainty is uncertainty because of some fact in the environment. Right? So typically, for example, if I, take a coin and toss it, the output can be heads or tails. No matter when I toss it, I do not know for sure what the output is going to be. Let's assume that you are building a model which could predict what the coin toss is going to result in. We'll end up predicting, we will always incur some error because 50% of the times our prediction is going to be incorrect. Right? So now if you have eleutaric uncertainty, if I am measuring prediction error, whether it can lead to an agent which is always curious about stochastic events. And what we saw was, an inverse model was one way to try to overcome this problem. I mean, there's a caveat, it works to some extent, but, we can come back to caveats in the end. So eleutaric uncertainty, the takeaway is that eleutaric uncertainty is problematic for prediction error based approaches. And many times what you want to do is to realize that, okay, this is an intrinsic property of the environment, and I can never accurately predict what is going to happen. Right? But then there's other kind of uncertainty, which is saying how confident I am about my model, right? Which is epistemic uncertainty. Now, I can always collect more data to increase the confidence in my model. Right? And I can say that I want to explore or collect data which is going to help me reduce the uncertainty in my model. So this is the idea behind bootstrap DQN. And so what they end up doing is they end up modeling the Q values, but they have K predictions of the Q values. And they construct a bootstrap estimate. Now, what is the bootstrap estimate? It's something we covered in a previous lecture, but I'm going to just talk about this algorithm in slightly more detail, and hopefully it will become clear. So instead of modeling one Q function, we are modeling K Q functions. And let B be the replay buffer in which we store experience, as is typical in DQN. So we start an episode. There is the initial state of the environment S0. Now, out of these K Q functions, we'll end up picking one of them uniformly at random. Then we will end up acting till the end of this episode using the K-Q function that we picked up on. Right? And how do we collect data with this Q function? We find the argmax to get the optimal action. Then we get a tuple of the next state, the reward on executing this action. Right? And then we can add this data back to the replay buffer. And now this data that is coming, we're going to use it to train a subset of these Q functions. And that subset is going to be given by a mask, which is a distribution which chooses if you have K dimensions, it would predict some of those dimensions to be 1, everything else to be 0. Right? So I might say these are the 3 Q functions which I want to update with this data. It's essentially implementing the bootstrap. So now, there are 2 questions which come up. One question which comes up is how many different estimates of Q values should we have? Right? So one possible, so they ran this experiment, and what they find is, on the y-axis, we are plotting the rewards. On the x-axis, we are plotting how many interactions the agent did with the environment. Red line is the DQN. What you find is that when you go from 2 to 5 to 10, right, as we are adding more number of heads, the performance is increasing. Right? So in general, it is good to have more number of heads, but having more heads also means that there is an additional cost. So at some point, the performance saturates. For example, over here, the performance saturates once we end up having 10 heads. Then the other question, we can have is that suppose if we collect data from one head, then how many of the different Q functions should I update? Right? Should I update all the Q functions, 75% of them, or 63% of them? It turns out it doesn't really matter that much. So what is these probabilities? These are probabilities of, when we're choosing this mask M, it is saying if I have 10 Q functions, how many of those Q functions should be updated with the data that I have just received, right? So I can say if the probability is 1, it means that I'm updating all the Q functions. The probability is 0.6. It means at every iteration, I was updating 6 out of 10 Q functions. So can you please tell what the bootstrap mask is again? So remember when we discussed about the bootstrap, so what does the bootstrap does? So bootstrap says, I'm going to take some data. Suppose I have a data set, then I'm going to sample one set of the data by uniformly and with replacement sampling that data set, right? And I can make K different data sets on which I'm training my K networks. Right? So now what I'm doing is I'm trying to make these different data sets. Right? And the way we are doing this is to say, well, each data point that I'm getting, I'm going to assign it to a subset of these K networks. This is the role what the bootstrap mask is essentially playing. It's helping us create these data sets for each of the K Q networks. Okay. Perfect. So now if you are aware of things like Thompson sampling, you can pretty much you can think of sampling one of the KQ networks as doing Thompson sampling. If you don't know about Thompson sampling, it's something I'm happy to discuss, but it's not required to get the intuition of what's happening in bootstrap DQ. But if you know about it, there's a connection which is maybe good to know about if you if you have studied Thompson sampling before. So next question is there a comparison of bootstrap DQN versus basic DQN with a really large batch size? What do you mean by a really large batch size? Do you mean when we're doing the Q-learning updates, let's just increase the amount of batch size and then do a Q-learning?
I guess it seems like a lot of the benefit here would come from almost like initializing these different heads, right, to enable like better kind of like exploration of this pretty kind of complicated, like large space of like Q function values, right?
Yeah.
But like I guess one alternative could just be to like really jack up the batch size, right? So that like you're getting kind of more like less noisy gradients at each step. Like I guess maybe one way I'm interpreting this method is of like decreasing the gradient or decreasing the noise of the gradients when you update the Q value. I don't know if that's like a good like way to look at it though.
So I think the goal over here is not to reduce the noise in the gradients, right? But the goal is to figure out, is to explore in the space of Q functions, right? So for example, consider, what I'm showing you over here is an estimate of the uncertainty, right? So where I have no data, I am going to be more uncertain. Where I have more data, I am going to be less uncertain, right? So these different Q networks will have different values where there is not enough data, right? So that will lead me to explore more.
So this is almost like a Bayesian method without like it's like a point-wise approximation to like having a posterior distribution or something like that, and that distribution just comes from having like a large K, and then you're like doing whatever like decision theory like on that approximate distribution.
Pretty much. So this is like a deep learning way of trying to be a pseudo Bayesian. So there's a nice paper by Balaji Lakshminarayan in 2017, which talks about how bootstrapping ends up estimate being very similar to doing a Bayesian uncertainty estimation.
Mm-hmm.
So if you're interested, I encourage you to look at that particular paper.
Gotcha. Cool. Thanks.
Yeah.
What was the author?
Balaji Lakshminarayan.
Okay.
Yeah, I mean, if you want, if you don't find the paper, just email me. I'm happy to point you to it. So there's another question, which is, the plot show reward of bootstrap DQN to be better than DQN. Is there ever a case where DQN should be used over bootstrap DQN? So let's, look at this comparison, head to head, bootstrap DQN versus, DQN. Now, we are looking at, two different, comparisons. One of them is showing the improvement in the best policy after 200 million frames. So what you notice is, in general, it ends up improving the performance versus, sometimes it might actually hurt performance. But the general trend is that bootstrap DQN is helping beyond, or it's better than DQN, right? So, to your question, Kylie, I think, in general, you should use bootstrap DQN to incentivize exploration. Sometimes the performance might not be as good, but those cases are not very common. Unfortunately, there is no theory which tells you that when should you use and when you should not use. In general, it's a good idea to use it, and there is empirical evidence that it's a good idea to do it. Did you have some other question, Kylie, or did I answer what you were trying to get?
Yeah, that was Thank you.
Okay. There's one more question, which is about what is the trade-off in trying to capture eleutheric uncertainty by training multiple Q functions versus training multiple Q functions with the same data set. So eleutheric uncertainty is something we cannot really capture by training multiple Q functions. That would be captured by training a probabilistic model. Like, for example, if you're aware of variational autoencoders versus autoencoders, so autoencoders are a deterministic model, whereas variational autoencoders are a probabilistic model. Right? Oh, so you meant the epistemic uncertainty. So what is the trade-off in trying to capture epistemic certainty by training multiple Q functions?
Yes, sorry if I can try to clarify. My question was, what if, to capture epistemic uncertainty, we may train multiple Q functions with different subsets of the data? Or what's the difference if we instead try to use the same data but initialize the Q function with different initial parameters?
So what has been found is that if you just change the initial parameters, and it's fine if you use the same data set, but you just uniformly sample the data set uniformly and randomly. Right? So each of those networks which have been initialized randomly just see the same data in a different order. That is sufficient. So if you want these experiments, it's in the same paper I suggested above. Right? This paper from Balaji Lakshminarayan, it has a good study. And the outcome and the empirical result is just having a different initialization and sampling data. And even if you sample the same data set, but in a different order, it works out, it gives you a good result of measuring uncertainty. And this is something that you see over here also, right? If my P is equal to 1, that means that just having good initialization is sufficient to get a good estimate.
Got it. Thank you.
So this was one way of how we can utilize uncertainty to guide exploration. Now let's look back into this prediction error-based uncertainty that we had discussed with this intrinsic curiosity module, which was built by taking features or states st and st+1 and trying to predict the future phi hat. Now, although what we saw was these algorithms can help us get a sparse reward faster than, say, training a vanilla PPO or an RL agent, we still required millions of steps for exploration algorithms to work. So when one big source of suboptimality is that the intrinsic reward is non-differentiable, right? What I mean is that I take this reward function and then we use reinforce to find the actions which optimize the reward function. So maybe if I can make the reward function to be differentiable, then we could potentially explore in a much more efficient manner. So this is the intuition which was realized by this particular work, self-supervised exploration via disagreement. So what they did was they trained n forward models instead of one forward model. And they measured the variance in the prediction of these forward models. Right? So I can measure how varied the predictions are. Right? And this is a good estimate of whether I should collect more data over here or I should not collect more data over here. And that is what they're going to use as the reward function. So more concretely, the reward is the variance in the prediction. Now, why is this differentiable? because this does not depend on the future xt plus 1. So if my reward depends on the future xt plus 1, then unless my simulator is differentiable, I cannot compute the gradient, right? Or I need to have a differentiable model of the world, right? If I don't have it, I can't compute the gradient. So now this completely removes the dependence on the future, right? And therefore we can differentiate through this and make it much more data efficient. Now this is a comparison that they did, comparing when we use disagreement with a differentiable way to optimize it versus using disagreement when we use reinforce to optimize the reward signal. And what we are plotting are the mean rewards on the y-axis and number of training steps on the x-axis. So what you see is that if we use the differentiable optimization scheme, the rewards increase in much fewer steps, right? Note that the x-axis is on the log scale. It is almost an order of magnitude faster. And this enabled, this particular work to apply this exploration method on a real robotic system to, figure out how to pick up objects. So that is one thing to keep in mind, that if you can make the reward function differentiable, it's going to work. It's going to be much more sample efficient than not having the reward function be differentiable. So you can treat this as, there are two things you can look at this. Right? One, you can think of this also as an example of using uncertainty to explore. And the other is this definition of uncertainty is differentiable, which makes my optimization be much more data efficient. So this is, one more flavor of an exploration method which has worked well in practice. Any questions over here? Nope. Okay. So let's look at another class of exploration methods which are based on the idea of counting. And counting, so what is the main intuition? The main intuition is that if I have not visited a particular state, then I should visit that state more often. Right? And this is something which is easy to implement in discrete or a tabular setup. It is also something that we have seen in multi-arm bandits. So recall in multi-arm bandits, we had an estimate of my reward, plus we had an exploration term over here, right, which was square root of 4 log t by ki, where ki was a count of pulling the ith arm. Right? So if I've pulled the ith arm more number of times, this means that my exploration term was low. Versus if I have not pulled the ith arm many times, my exploration term would be high. Right? So we were incentivizing less visited arms or less visited states. And this was the principle of optimism in face of uncertainty. That if I don't know enough about a state, which I can estimate by the fact that I have not been there many times, then let me go there because that state might be good. And then this was the optimal strategy for exploration in multi-arm bandits. Now in reinforcement learning, we don't know if this is the optimal strategy for solving the exploration-exploitation trade-off. But based on this intuition, one could include a count-based reward in my value function. Right? So we have put this beta times divided by square root of n, right? Where n is the number of times I've been to a particular state for my action. Now, what is the problem? The problem is that in discrete setups or in tabular setups, I can estimate this count. But what about in a continuous state space? How do we count? So there are, many strategies which have been proposed in the literature. I'm going to, show you two of them, and hopefully that will give you some intuition of how do we, count in a continuous state space. So the first method is as following. It says that let me take my state st plus 1, and I'm going to pass it through a random network. So I get a feature representation zt plus 1. Now let me again take the state st plus 1, but now pass it through a network with parameters theta, and I make a prediction of the features in the feature space z hat. And what I'm going to do is I'm going to try to predict the feature representation of the state through a random network. So I'm going to train this network to match the random features. So if I have seen a particular, so now assume there are two things which happen, right? Assume one thing is, suppose the mapping from state S to Z is 1 to 1. Let's assume that. And suppose that Z is much lower dimensional than state S. Then what's going to happen is that if I have seen state S before, then my prediction error is going to be less. Right? Why is that? Because that data I've already used to train. Versus if I see new data that was not in my training set, this prediction error is likely to be high. So in some ways, this is helping me estimate a probability distribution or the probability of this, of whether I have been to that state or not, in a non-Bayesian way. And we can use this error as the reward. In a way, it's a proxy for a count. So this idea is known as random network distillation. It's a proxy or a heuristic method to measure novelty or to measure whether I have been here before or not. And if you're more theoretically bent on why this might work, this has got to do something with the Johnson-Lidenstrauss lemma. Right? Now, what this lemma is beyond the scope of this class. But if you are curious, I would recommend reading this paper and reading this lemma to understand why random features end up being a good feature space. Any question on the intuition of what we are doing over here, right? I mean, another way you can think of it is that I could have measured, I could have done the matching in my state space st plus 1, but my state space st plus 1 can be high dimensional. For example, an image is very high dimensional. So essentially, these random features is just reducing my dimensionality to a low dimensional feature space, right? And because I'm in low dimensional feature space, this prediction task is much easier. Right? And it helps me know, or what do I mean by much easier? If my prediction space is low dimensional, it means that I require less amounts of data to learn the mapping from z hat t plus 1 to zt plus 1. Right? So if I require less amounts of data, it means that I'll get a better estimate of whether I've been to that state before or not. Because if I required, say, 1,000 data points to learn that, then 1,000 times when you come to that state, you still feel that it's new. But if I can quickly learn, then maybe after a few times, if I visit the same state, my error is going to reduce. And so therefore, it's good to have a low dimensional feature space, because that would mean I would require lesser amounts of data, which means that I would quickly be able to estimate whether I have seen this stuff before or not. But that's the intuition behind what's happening over here. Now we can use this method, which they call as R&D. Or, I mean, what was this method R&D? This method R&D pretty much uses this difference as the reward function. And we're going to compare it using two methods. One is a plain PPO, and one is this dynamics-based method, which is the prediction error-based method, which is shown in blue. So what you end up finding is that in many games, either R&D outperforms these two methods, or it ends up doing as good as prediction error-based curiosity. And there are more quantitative results. If you're interested in more of these results, look at the paper. Now, one of the hard exploration games in Atari is Montezuma's Revenge. Now, why is this hard? Is because the rewards are sparse. For example, this agent, needs to go over the skull, get a key before it opens the door, and you only get a reward, either if you die through the skull or you end up opening the door. Right? So it makes the game reward be quite sparse. And what this is showing is that if I just optimize this intrinsic reward, this agent ends up learning going from game, room 1 to room 2 to room number 21. And these are the intrinsic rewards as the agent is going to new rooms, right? So initially the intrinsic reward increases, it crosses, the room number 1. Then, again, you see a dip because it has learned how to go to room number 1. It starts entering room number 2, and then the rewards start increasing again. So it's starting to see some new things. And so therefore, you end up seeing, these decrease in the reward function, and eventually it ends up crossing a lot of the rooms. So, I mean, if you're looking for a hard exploration challenge, Montezuma's Revenge is one of, the hardest challenges in terms of exploration. And, this method got pretty good results on this hard exploration. Any questions on random network distillation? No? Okay. So now, let's look at another class of prediction or another class of exploration methods. So in this particular method, our intuition was that if I come to a new state, or if I have not visited the state often enough, then I should explore it more. Another notion is the notion of learning progress. Right? What is this? It says that if I make some error, when I observe an event A at time t, then I should incentivize the agent to take actions which lead to the event A, or those events A for which, suppose if I visit them t plus k times, then my error has reduced. And so suppose if something is very hard to learn, then and I try that many times, I'm still going to have a high error, which would mean the difference in my error is going to be low. But if something I am able to learn, as I am learning, the error is going to reduce, right? So what we are looking for are things that we are able to learn. And those are the kind of events or the kind of states or the kind of actions I should be incentivizing. And so that's the notion of learning progress, right? It's kind of related to what we discussed in curriculum learning, right? So one thing we discussed was we want to choose a curriculum in a way that choose tasks on which we're able to make some progress. Right? So similarly over here, we can say, if I have a model, let me choose actions where I'm able to improve my model. And so that's the notion of learning progress. But turns out this is hard to optimize in practice. Right? Now, why is it hard to optimize in practice? Is because you need to have an estimate of learning progress, at different time. So you need to have an estimate of errors at different time points, right, which becomes problematic. So one good result which came out was that learning progress can actually be equated with count-based exploration. Now, what do I mean by this? Right? So let's assume that we have a probability measure, which says if I give a state X, what's the probability that I saw the state X? Now, what we can define is a quantity called a pseudo count, which estimates the number of times X is seen. This is what we are defining. So, for example, the pseudo count could be, or sorry, this I can define this probability in terms of these pseudo counts, right? So if I've seen a state many times, it's going to have high probability. If I've seen the state less number of times, it's going to have less probability. Right? So n hat is the small n hat is the total number of observations. The capital N hat is how many times I've seen the state X. So let's assume that we observe X again. Now my probability is going to get updated according to this definition. Now, once I have this, I can estimate n hat in terms of the probability. So essentially, what I can do is if I had some measure of probability of X, I can estimate a count from that. Right? So, suppose I gave you a task and I said, estimate how many times I've been on the state. Right? And what you do is you say, well, let me build a probabilistic model which measures the probability of the event X. And now from this probabilistic model, I can estimate a count. And this is what we have done. Now let's look at the notion of learning progress or prediction gain. Right? What is learning progress? Learning progress is saying, let me look at the probability of this event in the future versus the probability in the past, right? Which is learning progress. It turns out this can be equated to the count also. Now, why is this an interesting thing? Because it says that I can use density models to estimate learning progress. Right? I can have a model of my data which is measuring the probability of that data, and from that probability, I can not only estimate the counts, but I can also estimate the learning progress. And that learning progress and counts are two things which are very similar to each other. So, this work unifying count-based exploration and intrinsic motivations from Mark Bellaway, which came along, 5 years ago. And what they're showing is, suppose I have this game. In this game, this chicken needs to, move from the the bottom of the road to the top of the road, and it has to not hit any of those cars. And what we are seeing is, how many times a new event is happening. And what you see is, right, whenever a salient event happens, this notion of pseudo count increases. Happens, the pseudo counts increase. right? So, I mean, the way to read this graph is to say whenever some significant event is happening in the game, we are able to estimate those counts. And again, they show result on a bunch of, different Atari games. And I think again, we can look at what happens on Montezuma's Revenge, which is one of the challenging games. So if you don't give any bonus, if you just train vanilla DQN, it only ends up going to 2 rooms. And with this bonus of learning progress or the counts, we end up exploring many more rooms. Again, the details of this work are in the paper, but I hope you got the main intuition of what this work does. So in summary, what we looked at, we started off by saying exploration was done using epsilon greedy. Or maybe let me backtrack, right? We, first in the course, we looked at multi-arm bandits. We knew that UCB gave us an optimal way to solve the exploration exploitation dilemma. And we saw how square CB helped in contextual bandits. In reinforcement learning, there wasn't an optimal method that is known. But there were heuristics like epsilon greedy and adding noise, such as adding Gaussian noise in continuous action spaces. And we said those are not good ways of exploring. So let us identify different approaches. So one approach that we looked at was using noise in the parameter space, which was noisy neural networks. Other class of approaches we looked at was based on uncertainty estimation. Right? So we looked at bootstrap DQN and we looked at disagreement. The third class we looked at was let's build a model which predicts what is going to happen. And the error of that model can be used to gauge what are the actions whose outcome I don't know about, and let me try to repeat those actions more often. Right? So that was the prediction error-based methods. Then we looked at an alternative to prediction error is to count how many times I've been to a particular state. Right? We looked at random network distillation. Then from curriculum learning, we had this intuition that a good way for the agent to discover new things is by measuring learning progress. And then what we saw was that learning progress and count-based exploration are equivalent to each other, or there is a relationship between them. And that is what this particular paper brought to the limelight. So that's, the family, that pretty much covers a broad family of methods for exploration. Of course, there are more things that people have tried. For example, some works have tried using diversity as a metric to guide exploration. And then you will find, different ways of estimating uncertainty or learning progress in the literature. Now, is there one of these methods, that one can recommend, which works the best? I think this field is progressing. So right now, I would say, like R&D was one of, or the random network distillation was one of the more recent papers, which in terms of raw performance seems to be superior to previous methods. But is the performance of one method consistently better across all environments? The answer is no. And that is an active area of research to figure out, can we come up with a consistent notion of perform well on, most environments. But maybe, this may not be possible because different environments might have different kinds of characteristics. And so depending on, whether in an environment it is more important to visit all the states, or Is it more important to have a model of how things work? The answer could be different. So, I mean, maybe what one can expect is, some characterization of the environment, that if this environment has these properties, one should use this exploration method. And I think having that kind of like a guidebook is something we can realistically hope for. And this is what the field is trying to get towards, but we are not there yet. So that's my last comment on these exploration methods. And happy to take any questions before we touch upon unintended consequences of exploration. So any questions over here? No? Well, then let's take, a small break, and let's, meet again at noon, and we will start, we'll restart at noon. Welcome back, everyone. So let's restart again. So a question I usually have is, can we use successor representations to do count-based exploration? You could, but the one issue is that successor representations are dependent on the policy. So what could happen is that, suppose there are two rooms, suppose there's a T-shaped, where the T divides into two rooms. So first, the successor representation might say, go to the left room, and then that might incentivize you to go to the right room. But once you go to the right room, then you might again go back to the left room and keep on flip-flopping between the two rooms, because you're not building a model of the environment which is independent of the policy. I think that is something key, that your model should not depend on the policy. Right? Otherwise, you will not be able to holistically know or measure what you know about the environment. Right? So if you looked at all the exploration methods, that they were independent of the policy, right? Whether you were measuring uncertainty, counts, prediction error, you were building a model separately from the policy. Does that answer your question? Maybe. Okay, perfect. Okay, so let's look at the unintended consequences of exploration, right? I mean, sometimes exploration can be undesirable. Well, what are some examples of this? And one example is, we have seen this before, that suppose I am a music recommendation system. Suppose there's a person who really likes symphonies, and Spotify has, say, suppose they have a reinforcement learning algorithm, working on the back end, which is trying to suggest more music to keep this person hooked. Right? So to explore by suggesting other music. Now, if I end up exploring a new music, and suppose we recommend Lady Gaga, which is pop, maybe this person only likes classical music, and when we suggest pop music, he might start hating Spotify and may not come back, right? Or assume, Netflix or Amazon Prime, ends up recommending you, movies which you don't end up liking, right? So you cannot uniformly explore everything. The exploration needs to be constrained at times. Like similarly, if you have real robotic systems, we may not be able to explore everything. I might feel that the action of falling down, if I fall down, I'm going to make a big prediction error because I don't know exactly how I'm going to fall down. But, falling down is bad. You might end up breaking the robot. So what do we do in these situations? Right? So one thread is the thread of safety, of safe exploration. But for now, we are going to use another thread, which is saying, suppose if online data collection is not practical, then can we take the data that we already have, right, some big data set from past interaction? Now, this could be, for example, medical records which already exist, but I don't want to carry out new experiments with medicines because that might harm the health of someone. So new exploration is very expensive, but we have a big data set from past interaction. Or for example, I built in a safe controller on the robot, which I knew was safe, and I collected some data from it. But now I have new tasks that I have to train for, so can I train it? So this is what we'll end up studying as part of offline reinforcement learning. So just to give some context, so online reinforcement learning is the setup where we are collecting data, update the policy, we collect the data, and so on. So this is what we looked at on policy. So this is online reinforcement learning with on policy algorithms. Then we looked at off policy algorithms. And these algorithms are like DQN, DDPG, SSC, all these algorithms had a replay buffer, right? And this buffer could have gotten data from the current policy or from any other policy. So instead of sampling just from the environment, we sample from a buffer. But we still take actions in the real world. In offline RL, the setup is a bit different. So there is some data that is collected only once. Then we have a buffer and we learn a policy, right? There's no arrow which goes from the policy to collect more data in the real world. Right? And then we just deploy this policy in my new environment, my new task, or whatever is of interest. So that is a key distinction between off-policy reinforcement learning and offline reinforcement learning. Okay. Any questions? No. Okay, so I hope this is clear because we are going to look at offline RL algorithms. So if the distinction is unclear, feel free to shout out now and clarify it. Okay, so let's see, what is one simple strategy we can use to learn in this setup? Anyone? What could we do? What is the simple strategy we can use? I have, a buffer of things, and I want to learn some policy from this data set, and I want to deploy some model-based RL. So now if you look at a lot of the model-based RL work, so one thing you can say is, well, I can learn a model with this data, and then we can use this model in my deployment scenario, right? So that is one possibility. Other possibility which has been suggested is learning from suboptimal demos, which is doing some kind of behavior cloning, right? And there's another suggestion which is meta learning. So let's stick with the behavior cloning or the learning from demonstration scenario for now. And let's come to the model-based and meta learning aspects later on. Right, let's start from there. Why am I starting from behavior cloning? Because it's the most straightforward thing I can do, right? I have a data set of states in action. I can just do supervised learning to get a policy. But, I'm going to make a claim that performing behavior cloning and just deploying it is not a very good way to learn in an offline RL set. And the question is why? And for this, we have a poll. So now you should be seeing this poll. So one thing to note is that this poll, you can choose multiple options. This is not, multiple options can be true. So if you think there are multiple choices, then, choose multiple of them. So there are, yeah, so we are, is it the covariate shift problem? Is it the behavior cloning policy just mimics the data set and does not improve on it? Right, so just read those options and then make your choices. Let's give 30 seconds so you can just understand the options and vote on them. So I see that we have gotten 11 votes. We're waiting for 6 more. I think, now if you're on the edge, make your choices. We're going to end in 5 seconds now. 5, 4, 3, 2, 1. And, anyone who wants to make the last choices, let's end the poll. Let's see, what everyone said. So what we found is, most of us think there's a covariate shift problem which can happen during deployment, which is true. This can happen. The other is it simply learns to mimic the actor in the data set and is unable to improve it. And there's a fourth option, which is it can learn an optimal policy in the training phase, but fails to transfer during deployment. So these two options are related, but there's a difference, right? So if my expert is suboptimal, then just plain old behavior cloning is not going to improve upon that suboptimal expert, right? For the option D, that it can learn an optimal policy, right? That assertion is not really true, right? It's not about the problem of transfer of an optimal policy. Right? There's a problem of transfer, which is the covariate shift problem. And there is the problem that I might never be able to learn an optimal policy. And about data for training, I think, we will require data for training, but let's consider that we have some finite data set and we are trying to see what is the best that we can do. So let's understand, what do I mean that we cannot learn an optimal strategy from the data? And the reason for that is that behavior cloning is not doing dynamic programming. So it cannot learn the optimal strategy. Now to see this, consider an example where suppose a human, just was playing around with this environment and we recorded the state action trajectories, right? So we have a data set. Now suppose in this data set, the kind of data that we end up collecting is we go from state A to state B, and sometimes we go from state B to state C. Now, if I have to go from A to C, then going from A to B and then from B to C is suboptimal. And maybe we can stitch them together and know that there's a path which can directly go from A to C. And so I don't have to go through B. So this is what dynamic programming helps one do, right? It helps one stitch things together, which might not be apparent in each individual trajectory by itself. Something that we touched upon in prior lecture, when we were looking at motivation for reinforcement learning from a dynamic programming perspective. So, the takeaway being that, behavior cloning is straightforward to implement, but it might end up learning a suboptimal strategy, and there's a covariate shift problem. So one question we can ask is, how can we overcome the suboptimality? So one reason for suboptimality was that we are unable to do dynamic programming and behavior cloning. So this might suggest, how about we just run off policy RL? Maybe this is going to solve the data. I mean, why do I can just treat this replay buffer. I mean, we know how to take data from replay buffer and train a policy, right? SSE, DQN, they all do this. Why not? Let's suppose we have a data set and we run some off-policy reinforcement learning algorithms such as SSE. But unfortunately, what we find is they don't end up working that well. And the question is, why? So one possibility is that maybe this data set is small. and therefore, off-policy algorithms fail. So in one of the papers in the literature, they looked at this question: is this overfitting happening due to a small data set, or is the bad performance due to a small data set? What they did was they ran an experiment on this environment half cheetah, but with different number of data points. What you end up finding is the performance doesn't really change depending on the number of data points that are there. So the point being that the poor performance of running off-policy algorithms is not due to the fact that the amount of data which they have is small. That is not the primary reason. And the other thing that they also end up finding is that as we end up training more, actually the Q function ends up degrading. The Q function degrades with more training. Now you might be like, why is this happening? And the reason this happens is because of distribution shift. Now, what do I mean by distribution shift? Let's try to look at that. Now, in Q learning or in off-policy learning, typically when we're doing off-policy learning, we are using Q learning. So, when I'm doing my Q learning, I'm taking my data, but this data is coming from a policy, or this data is coming from my data set, right? Which is my behavior policy, which was used to collect this data. And then I'm learning my Q functions, and my Q functions are supposed to match the target value. And this target value is typically the reward plus the expected Q value of the next state. So one thing to now note is that when there are two different policies over here, right? So one is pi beta, which is the policy from which this data is collected, and one is pi theta, the policy that I am learning, right? And the claim is that when pi theta and pi beta are different, the estimates of target value are incorrect. Now, why is this? Let's consider an example. Suppose the data I have is I'm in state S. We take an action, we reach state S prime, and suppose we have such a data set, an existing data set of n examples. Okay. This is the typical Q learning update that we have, where this B is just a Bellman operator. Now, suppose we did this Q learning and we got this policy mu. And now what we do is, we take this policy mu to estimate my target. Right? So I have to estimate the target for my Q learning. And I feel that, in state S, the optimal action might be A prime, which I sample from this particular policy. Now, the target I'm going to compute is going to be the Q value of S comma A prime. But S comma A prime might not be in my data set. Right? Which means that I can overestimate this value. And because I don't have any data for this particular state action pair. Which means that if I'm overestimating the Q value, I can learn a bad policy. So sort of what is the problem? Right? The problem is I'm in some state, I take an action, I reach S prime. Now suppose I end up learning that the Q value of S prime is low. But if I take A prime, I don't have any data on what the Q value is going to be. Right? So I might say in state S, the optimal action is A prime, but this is based on a wrong estimate. Right? And there's no way that I can verify whether this estimate is right or wrong, because I cannot actually execute A prime in the real world. So another thing to recall is when we were learning about Q value estimation, what we noticed was that Q values are often overestimated. Right? So now there is overestimation of Q values, and we cannot correct that overestimation by acting in the environment. So just running off policy RL leads to overestimation in Q values, which leads to a bad policy. Like, why is it not a problem in typical off policy, RL setups? Because we are still doing some online data collection with off policy RL. And you have a replay buffer from which you are sampling to update a queue function, but you're still interacting in your environment. Right? So you'll be able to correct these overestimation errors by collecting more data. Is the problem clear? Why just running off policy algorithms on an offline data set doesn't work out of the box? Yes, no, maybe a raise of hands, or maybe just type in yes if the setup is clear or the problem is clear. Okay, it seems like there's some feedback. Great. So if you want, a one-line summary of what offline RL works are trying to do, they're pretty much just trying to solve this challenge. How do I remove overestimation in Q values? Right. So this is the central problem solved by offline RL algorithms. And let's look at how they are doing. So, we had this Q function, and this is just my Q learning, what I've written down, the target, how I learn my Q function. And from the Q function, we end up estimating my points. So broadly, there are two classes of algorithms used to overcome this overestimation. One is to constrain the policy space, which says that, well, don't really take actions which are not in my data set already. Right? So pi beta is the probability of taking the action A from state S, which I estimate from my data set. Right? So I have a data set of state actions. I can estimate this probability. So one thing I can say is, always be close to my data distribution. And we know how we can include these constraints, right? We saw in PPO, how it's very easy to include the constraint where D is a distance function and D could be, say, KL divergence. Right? But D could take other forms, like it could take MMD and so on and so forth. We're going to look at some of these forms shortly. So this is one possibility. I have my argmax plus, or I add this penalty that says find me the policy which maximizes the Q function but still remains close to my data. That is constraints in the policy space. The other set of methods are what constrain in the value space. So they don't try to put constraints in the policy, but we are adding a small reward term which is incentivizing the policy to remain as close to my data distribution as possible. Right? So add a reward to encourage the policy to stay close to the data distribution. Think of this, similar to adding an entropy bonus in SAC. Right? We add an entropy bonus to incentivize exploration, or how we were adding intrinsic rewards. Right? You can as well as think of Q is your extrinsic reward estimate, and this is my intrinsic reward. Right? So we are pretty much saying policy, instead of putting an explicit constraint on the policy, we're implicitly biasing the policy to remain close to my data distribution. So we are going to look at both of these methods. Now, one challenge in both of them is that we need to estimate this data distribution pi beta. Now, in some cases, it is possible to do this in a straightforward way. In some cases, this itself can become challenging. So if you want a good discussion on how to estimate pi beta, either directly or there are some methods, or you can also use adversarial methods using F divergence. So these are some, as an advanced topic that you can look in this paper. So for now, we're going to assume that we can estimate pi beta and look at these family of methods. But if you want a more advanced discussion, look at this particular paper. So let's look at one of these methods. So this is known as bootstrapping, error accumulation reduction, or BEAR. So what they do is they simply say, first they use the trick of double Q learning, right? That if I have to remove my bias and overestimation, let me have KQ functions, choose the minimum of them, right? We read about double Q learning where we had 2 Q functions. Instead of having 2, you can have K. Okay? So that's one thing that we're going to use. Plus, we're going to introduce this constraint that the policy that I am learning should be close to my data distribution. But instead of using KL divergence, we are going to use this another measure called MMD, which is maximum mean discrepancy. Now, what is this? It's some distance measure, or you can think of this as covariance, but in a kernel space, right? And this kernel function could be Gaussian or Laplacian or so on. Now, if you know about kernel functions, you'll instantly get what this is doing. If you don't know about kernel functions, don't worry, just think of MMD as a distance metric, which is imposed. So there are different papers which use different distance metrics. So there's one paper which uses scale divergence. There's another paper which uses this. There are other papers which use some other distance metrics. And then they compare against each other. Another possibility is, in this other paper called batch constraint Q learning, or BCQ. What they can do is, first they estimate this pi beta that we were talking about, which is represented by this GW, which is a generative model of actions that we learn from a data set. Now, if I sample from this, I'm going to get actions which are close to my data set. But, we do need to explore beyond my data set, right, to form these shortcuts, which will enable us to improve the policy from just copying what the expert did. So we're going to perturb this action A by some small amount, psi. The question is, how am I going to choose this psi? And the psi is a function of this parameter phi, right, or phi. So how to determine phi? Well, we can say, let us choose this parameter phi so that if I perturb the action, it gives me the maximum Q value. Now, what's the trouble? The trouble is that if I end up choosing an action which is very far away, then this Q function is going to be an overestimate, right? Because of the overestimation bias. Now we know from double Q learning we can mitigate this. So what they do is they use the double Q learning thing where they have this function Q, or they have 2 Q functions that they're estimating. And this can remove some of the overestimation bias. In practice, what they find is just using double Q learning to choose phi can make this algorithm be very conservative. So to trade off how conservative we can add one more term, which is just choose the maximum of the Q function. But now we have to trade off between how conservative and how aggressive. And typically this value lambda is chosen to be more than 0.5, which means, be conservative mostly, but try to be somewhat aggressive. how this lambda is tuned, it's a hyperparameter. But I hope, you're getting an intuition of, what we are doing, right? We are trying to model the data distribution and trying to change it, by a small amount. Now we can see, some results over here. So we are looking at two environments, Hopper and Walker. The y-axis is the rewards and the x-axis is number of training steps. Know that we're not collecting any more data. Right? We're just going to more training steps, means how many times I've trained on my data that is already there. So the blue line is just training SSC. Right? The yellow line is doing behavior cloning. Then we looked at this BCQ and BEAR, which were two ways of considering the policy. And then what you can see is they end up improving the performance on top of SSC or behavior cloning, which is these lines in green and orange. Then the scale VP is putting a value penalty, which is exactly as we wrote, just putting an entrance, taking the KL divergence between the policy and the data distribution, and including that as the intrinsic reward. It seems like this value penalty does better than doing a constraint in the policies. So this paper in 2019, they did a thorough study comparing, for example, if I use the MMD distance function, but if I put the constraint either on the policy or the value function, which one of them works better? The conclusion is that value penalty seems to be outperforming policy regularization. So I'm going to stop over here, and the next lecture we're going to pick up on the latest and greatest method for putting the value penalty constraint. And with that, we're going to stop. I'm happy to take